This conference is brought to you by Callstack, your React and React Native development experts.
Hello everyone, we are here to present you our solution for unified and extensible tracing in React Native. First, we would like to introduce ourselves. So my name is Artur Morys-Magiera and I work at Callstack as a senior React Native developer.
And my name is Dominik Dolny and I work at Callstack as a senior Android developer. Today, we'll explore two critical areas that most programmers are familiar with, but we'll examine them specifically through the lens of React Native: performance and observability. Finally, we'll share a solution we designed to help you overcome these challenges in React Native applications. For the sake of this introduction, suppose you have a component that is deteriorating the performance of your application. You have started investigating it and identified the problematic component. It turns out that its hook takes a long time. So what now? How do you identify which block or function takes the most time and should be optimized? You could try a trial and error approach, or you could use a more sophisticated tool. What's blocking you may be an asynchronous operation, such as an event, network request, or queue. The same applies to code written in C++, Kotlin, Java, Swift, and Objective-C.
Advanced use cases could also include tracking of requires impact on app or screen startup time. It would be awesome if you could simply view a flame graph showing the time each module took the interpreter to load. Another example could be tracking of React Native internals. If something worrisome is happening, for instance due to side effects from your JavaScript code. This is certainly a more advanced use case, but sometimes it may be the case. For instance, it can be useful to view how component renders affected the native view's render time. So, how can we enable tracing of React Native internals? Firstly, by default, tracing is disabled for all platforms and languages. In order to do this, you can build from source, performing some modifications. On the Android platform, for instance, you can enable tracing from Java and JavaScript APIs by flipping a constant in its Kotlin sources, but you still need to recompile. And there's one more thing. React Native has already been providing prebuilt artifacts for Android builds, but recently it was also announced that on iOS, starting from React Native 0.81, there will also be precompiled binaries provided. This is a very useful optimization that will help the great majority of developers, but for some niche cases, like the one I mentioned, this means modifying React Native core to add instrumentation will be harder on iOS.
Returning to the Android case, you need the proper preprocessor definitions to enable tracing of the C++ code. Finally, React Native already has instrumentation in many locations, which will now be enabled. However, if you need tracing elsewhere, you will have to instrument it manually. The next step is to configure your app to use the local React Native build. And even more changes are required. Then, build and publish React Native. Wait for it.
So, are we there yet?
Well, kind of, but not quite.
So now let's review what we have done so far. We have a React Native app that builds. It has instrumentation in place. We can trace both React Native internals and our custom code wherever we place our instrumentation. We are limited to recording the traces using the tool integrated with React Native of our choice that we have enabled. And the consequence is that we need to use the corresponding visualization tools, such as Perfect2UI in the case of Android. After we iterated that, let's explore the challenges that a perfect solution would need to tackle. Since React Native involves many languages, this is JavaScript, Kotlin, Java, Swift, Objective-C, C++, and multiple platforms apply integration with different libraries and tools, helping to achieve equivalent outcome on different platforms. As a consequence, we will have a variety of data sources, which bring even more complexity in. React-specific features will also need additional handling. For instance, we may want to track React component lifecycle, networking, device information, and similar things.
Now, let's review a few examples of what to trace. You can trace selected React components to obtain information about the performance of their renders. Tracing hooks may reveal states in which they underperform. Network tracing allows you to identify unnecessary, failed, or excessively long network requests. Tracing navigation allows you to see everything the user did before the events we are viewing took place. This helps us partially reconstruct the app's state.
Each of the data sources, like ones we mentioned, needs an external sink. The data sink is the actual destination where all the traces, all the collected data will land in. For instance, this could be a database or a visualization tool of our choice. For production, this may be an API client or a telemetry SDK. However, for development, usually profiling APIs are native, implying the needs, for instance, for a Turbo module. So what if we had something that wouldn't require us to rebuild React Native from source, however, would also cover the production observability needs and give us more tracing flexibility?
We present our solution, a library that provides a common tracing API and integrates with React components and React Native as a platform. No React Native build from source is needed. The tracing backend system is pluggable, meaning you can implement your own data sync for the traces. Ottrelite provides solutions for both development time tracing and production time telemetry. More information on these solutions will be presented later. We provide hooks and Babel directive for integrating with components and hooks. For advanced use cases, the imperative API is available. Ottrelite provides a common interface that must be implemented, which allows for the integration of any backend for traces. The library provides a JavaScript API. An equivalent API is available for Kotlin and Java via JNI. The library also provides an API for C++ and for Swift. The actual implementation is written in C++ only. All other languages only provide interfaces. Therefore, calls from all languages land in the same implementation.
So let's go to practice now. First, we'd like to show you a demo of how to trace your code using Ottrelite. The demo application to the right, which is available in our repository that we'll show later, will be used to demonstrate tracing. On both Android and iOS platforms, we provide multiple backends, and one we provide wraps a profiler, an open source profiler named Tracy, which you can see to the left. And as you can see, we will open a demo screen. You will be able to see the traces live to the left, along with some metrics like CPU usage. Currently, what we are showing you is our manual instrumentation of the screen. So we will be able to see all the sub-procedures of this image that we can see to the right, how it has been generated. As you can see, we also support some features like showing the origin of the trace. For instance, here is the JavaScript API trace. We also have event metadata, any key value pairs that you would like to also include with these events, a stack trace. And as you can also see, we have the hierarchical view of what was called from which function. Another interesting feature that's specific for Tracy is that it provides statistics. So you also have this out of the box. This way you can view the runtime of this function in front of other runtimes this function was invoked. And now a second demo screen on which we provide the JS API. So here we are simulating some heavy computations. We actually delayed this a bit with a slip. And we are also doing something else. We are also tracing numerical values with so-called meters or counters, depending on the tool we are using. This is different nomenclature. And this allows you to basically trace your numeric values within time as a time series. This is also supported on Tracy and other backends as well. Another backend that we implemented, the platform backend, uses a tracing API specific for the platform that we are running on. For iOS, this is the OS signposter API, traces from which can be viewed in Xcode instruments that we can see to the left. In the case of Android, this is the ATrace API, and the traces can be viewed either in Android Studio Profiler or in a tool called Perfetto. As we can see, we have very similar functionalities. However, here in instruments, we also have the separation into different lanes depending on the category or the origin language from which the trace was created. Having said that, let's take a look at tracing in Android Studio using the built-in profiler. We will do a very similar thing. So first, let's try the same image generation demo in C++. Then we will start recording. We can resize the image to generate it again. And then we will do exactly the same, but this time from a Kotlin Nitro module, because we are using a Nitro modules under the hood in this example, to do this from Kotlin. As you can see, the same traces will be visible in the Android Studio Profiler, and you also will be able to preview things like the statistics, the count, the average, max, minimum, and standard deviation of the time this function took to run, as well as all other invocations of it in the recording. So how can you get started? Well, simply you will be able to install Ottrelite core and selected backends, and then invoke the install methods, and you will be set. We also may be interested in tracing of React components, for instance, their life cycles, and we will be able to view them in the traces within contexts and specific information we would also like to attach to the events. So we also provide a Bubble plugin that will automatically instrument your components by injecting instrumentation code into them whenever you use a proper directive. The instrumentation is both for production use cases, and we will cover that later, as well as it will invoke the development API for development tracing needs. To get started, you have to install the plugin and simply configure it in your Bubble config.js, and that will be it. To auto-instrument the component with our hook, you'll have to use the useTrace directive. The directive, of course, will support both function components and class components. For more advanced use cases, for instance, if you want to attach some additional metadata to the events, we provide a hook called use component render tracing, which allows you to specify both the name of the trace as well as the metadata. This hook can be configured to either invoke the development API or interoperate with a production-grade library that I don't want to tell you about now. We will cover this in a second. The hook will trace both the actual render time that the component really took in React Native to render on the screen, as well as the length of the JavaScript logic that it took to run before the actual native render. And this second value will be traced as an attribute of this span, as you can see here. You can also use Ottrelite's development API, which provides a few imperative methods of use, as you can see to the left. And what's important, the API's interface is common for all languages. This is to address the needs React Native developers usually will have, as we have said previously. So for C++, you will only need to include the Ottrelite.hpp header, and you will be able to use a very similar API to what we've seen in the JavaScript API. The same will apply to Kotlin and Java, where you will need to use the Ottrelite Android object.
But how did we address the need to build React Native from source? Let's take a look at a piece of code from Systrace.kt, which is a part of React Native's performance tracing infrastructure. As the code shows, the particular implementation has some significant limitations. Notice how many values are hard-coded. This means that to enable tracing, you must modify the core file directly. Due to these hard-coded elements, it becomes challenging to plug in new tracing behavior or adapt existing ones without altering the React Native source code. Now, let's explore a power technique for modifying application behavior after compilation, bytecode manipulation using framework called ASM. ASM is a Java framework that allows us to read, analyze, and rewrite the compiled bytecode that Android's ART executes. As you can see on the slide, our source code is first compiled into bytecode. ASM steps in at this stage. Think of ASM as a toolkit that lets us programmatically open these .class files and make precise changes. Why is this critical for our tracing scenario? Our primary goal is to enable tracing dynamically. Let's start with the isTracing method from the previous slide, which normally returns false. Using ASM, we can locate this method in the bytecode and alter its instructions so that it returns true, which activates tracing capabilities. Additionally, ASM allows us to do more than just flip a switch. We can inject entirely new bytecode sequences. This means we can insert custom tracing calls directly into existing methods without touching the original source code. We've seen that ASM can modify bytecode, but how can we apply these changes consistently and automatically within our project? That's where Gradle comes in. Gradle is our build tool that allows us to integrate ASM transformations through a custom plugin. While Gradle compiles our Java or Kotlin code into .class files, our ASM-powered plugin has the opportunity to process these files before they are packaged into the final application. This is where our ASM logic is applied. Gradle ensures that ASM transformations are applied every time you build your project. No manual intervention is needed, and the bytecode instrumentation becomes an integral part of your standard build lifecycle, delivering an instrumented application ready for tracing. Here is a snippet of a core component of ASM called method visitor. It gives us precise control over the instructions within a specific method. This code snippet shows us we can use a method visitor not just to tweak, but to entirely replace the body of an existing method. The goal is to replace the original method's instructions with our own custom bytecode. This could enable specific tracing, alter behavior, or even stub out a method entirely. When ASM processes a class, our custom method visitor is essentially called for the target method. Rather than passing through the original instructions, we instruct it to write a new set of instructions that achieve our desired outcome. Here, we are replacing the end section from systrace.kt with the end section method from Ottrelite Android. One valid question that might arise is, what happens if React Native updates its internal code? Could these modifications to the bytecode cause crashes or break the app? This is a critical concern, and we've designed our approach with it in mind. First, our instrumentation techniques are designed to be as robust as possible. If something changes in the React Native code, the worst that can happen is that the code won't trigger Ottrelite Android methods. There is no possibility of crashes or unstable behavior. We actively monitor React Native classes, releases, pull requests, and discussions to stay ahead of changes that could affect our instrumentation.
Finally, now, where do all these traces land in? The answer is, you can bring your own backend. The tools we have shown you previously in the demos are wrapped by Ottrelite backend packages. So let's reiterate that. The platform backend uses ATrace on Android, which you can view in Android Studio's profiler or in using Perfecto UI, which is presented in this slide. On iOS, this happens through the OS Signposter API, and the results can be viewed in Xcode instruments. Events are separated by category and origin on different lanes. The last backend that we demoed was a wrapper for the open source Tracy profiler client. Tracy visualizes live traces streamed over the network, is able to plot the statistics, and we also support metadata, stack traces, and numeric meters.
There is one last thing we would like to present. We explained how to debug problems during the development stage, but Ottrelite also performs well in production scenarios thanks to its interoperability with OpenTelemetry. OpenTelemetry is an open protocol that standardizes the format in which trace and metric data is exported from your application. Many tools, such as Grafana, Jaeger, and Prometheus, support its OTEL protocol, allowing you to stream your data to popular storage, analysis, and visualization tools.
We would like to show you an example of how Ottrelite integrates with OpenTelemetry and allows you to instrument paths in your code, once both for production time and for development time live preview in Ottrelite's backends. We prepared 2 demo screens. So let's see how it actually works. So the first screen uses the OpenTelemetry JS API, and it allows us to normally use the OTEL. We will be able to view all the traces in a tool of choice. For instance, here we show Jaeger. We will see that all the tags regarding the device specifics, as well as our custom tags, are visible. And we also have a screen where we do automatic instrumentation using our Bubble plugin. And we will be able to view this here as well. We also see the JS logic duration attribute that I mentioned earlier and the actual native render time of this component. And finally, the last part, that is the whole time, the invocations from the OpenTelemetry JS API were also intercepted by the interop layer with Ottrelite and were at the same time traced in development to a backend of choice. Here we chose Xcode instruments to demonstrate this to you. Exactly the same traces that we have seen in the production-grade tool for OpenTelemetry have also landed in our development backend. With Ottrelite, you would still configure OpenTelemetry's JS SDK as usual, but you will also need to change a few things. The first is to use Ottrelite's tracer provider and the tracer meter, the meter provider. The second step is to set up Ottrelite's span processor interceptor. This is an important step that allows Ottrelite to actually pipe the OTEL spans to our development backends. And there is also one optional step that you don't need but could use. That is also initializing our exporter. Currently, we only provide one for OTLP HTTP, but this will be extended in the future. And what this does is it actually configures not only the JS exporter, but also a C++ one. So this means with one line of code in JavaScript, you're able to share the configuration and initialization in both JavaScript and C++, and also potentially utilize OTEL CPP in your native code. And soon in the future, we will also integrate this with the Swift and Java/Kotlin SDKs for OTEL.
Okay, so let's sum up what we learned. Ottrelite is all-in-one solution for development, profiling, and production monitoring. It offers quick and straightforward integration without significant overhead.
It's extensible with a common interface so that you can bring your own backend of choice. It offers tracing of React Native internals without having to build from source and to worry about internal changes.
Tracing is possible in all languages via a common API. We provide integration with OpenTelemetry JS and C++ SDKs, and there is only one configuration in JS. We plan to integrate it with Java and Kotlin and Swift SDKs in the future.
Ottrelite also provides a wrapper around the C++ OpenTelemetry exporter so that you can configure it once from JS and pipe plans from all languages to this single exporter, sharing a common exporter instance and a common connection. Please also feel free to browse the app presented in the demos in our repository on GitHub.
Thank you for your attention. Stay tuned for updates and the upcoming release.